Welcome to a summary of the derivative rules. So at this point in this chapter, we have seen quite a few derivative rules and should be able to take the derivative of most functions that we see. I'm just going to go ahead and run through all of the various rules that we have seen so far. So suppose that f and g are differentiable functions. And then a, c, and n will be real numbers, a greater than 0 and n not equal to 0. So first up, we have our scalar multiple rule. If we wish to take the derivative of c times f of x, this is just c times the derivative of f of x, or f prime of x. Next up is our sum difference rule. If we wish to take the derivative of a sum or difference, we can just split the derivative across the sum or difference. So the derivative of f of x plus or minus g of x will be f prime of x plus or minus, whichever we're working with, g prime of x. Next up, we have our product rule. So if we wish to take the derivative of f of x times g of x, we do the derivative of the first, f prime of x, times g of x. And then we add the first, f of x, times the derivative of the second, times g prime of x. Next up, we have our quotient rule. The derivative of f of x divided by g of x. We do the derivative of the first, f prime of x, times the second, g of x. Then we subtract the first, f of x, times the derivative of the second, g prime of x. And then divide the entire thing by the denominator for the second, g of x, that whole squared. Next up, we have our chain rule. If we wish to take the derivative of f of g of x, this was equivalent to taking the derivative of f with respect to that inside function, and then multiplying by the derivative of g with respect to x. Next up, we have just our basic derivatives. If we want to take the derivative of a constant, that is always 0. If we wish to take the derivative of x, we wind up simply getting 1. The derivative of x to the n was nx to the n minus 1. That's our power rule. Again, this is for all n other than n equal to 0. The derivative of e to the x, this was our special function. It spits out itself. We just get e to the x. The derivative of a to the x, generalizing to exponentials where a is positive. We get the natural log of a times a to the x. Derivative of natural log of x, we've seen previously, was 1 over x. The derivative of log base a of x, we were able to figure out using our derivatives of inverse functions. We found this was 1 over the natural log of a times x in the denominator, or we could do 1 over natural log of a times 1 over x. Next up, we have the derivative of sine, all of our trig derivatives. Derivative of sine is cosine of x. The derivative of cosine was negative sine of x. And the derivative of secant x was secant of x times tangent of x. The derivative of cosecant of x was negative cosecant of x times cotangent of x. The derivative of tangent of x was secant squared of x. The derivative of cotangent x is negative cosecant squared of x. And then finally, we have our inverse trig functions, which again, we saw now that we can take the derivative of inverse functions. The derivative of sine inverse x was 1 over the square root of 1 minus x squared. The derivative of cosine inverse was negative 1 over the square root of 1 minus x squared. Again, these are just on the domains of our inverse trig functions. Next up, we have a derivative of secant inverse was 1 over the absolute value of x times the square root of x squared minus 1. The derivative of cosecant inverse is negative 1 over the absolute value of x times the square root of x squared minus 1. Derivative of tan inverse is 1 over 1 plus x squared. And the derivative of cotangent inverse of x is negative 1 over 1 plus x squared. So those are all of the derivatives and derivative rules we've seen so far. And if we put all of these together, it should enable us to take the derivative of pretty much any function that is thrown at us, or at least any differentiable function that is thrown at us.